So hello everyone, again welcome to this lecture. So in this lecture we are actually proceeding with the neural network. Okay, so this is actually the completely different topic whenever you wanted to understand about the deep learning section. So the neural network is basically the building block of it, right? So in order to understand any machine learning part, there is two way. The one foundational traditional machine learning course that we have done before, and now from here we are actually starting our deep learning journey. Okay, now from here I'll give you some content that what are other things that we are supposed to do. First of all, we are supposed to understand the architecture of neural network, and from here we will be starting it from the very basic part, right? So we will be starting with the neural network, the architecture of the neural network. Okay, then how the convolution neural network works, because we are mostly using it into the image processing part, right? So we will be again dealing with a lot of OpenCV libraries and doing a lot of image processing in front of you. I'll show you the in-hand demo as well, and then we will proceeding this video with the YOLO detection model and other kind of a model which is mostly focusing on image captioning, the image generation, the image detection, and other part of it. Okay, so the entire video lecture, from this I want you to be a little more conscious about that how you actually learning the neural networks, because neural networks is basically a very building block, right? So in order to understand the neural network, we will be first starting with the journey. Okay, that how the neural network has developed, and till up to this time, right? So how it is actually evolved, and how the AI engineers are basically utilizing this form of tool so that they can actually train the model more regressively and more smoothly. Okay, so neural network is it's basically a subset of the machine learning part, where there is a complete environment of deep learning section, and inside a deep learning section we will be learning about all these things. Okay, so I hope that in next of the video lecture we will be again doing the theoretical part. So I will cover all the theoretical part which is actually needed, and I think forfeit in any other dimensions, right? And then we again go with the implementation part as well, right? So I hope that you catch up till now, and then let's go with the another video where I will be starting with the concepts of neural network. Thank you. So hello everyone. Let's start with the neural network basics. Okay. So I think this is very favorite topic. I think this is in fact my favorite topic as well when it comes to deep learning, because the neural nets is similarly it's more of a how your actually brain works, right? So it basically started in the area in the year of 90s, where people started using a biological neural network, right? So BNN, right? So they wanted to transmit some kind of a message, right? So, and these are actually the neurons we have, right, in our brain cell. So let's say that they wanted to transmit something, right? So neurons is actually the very best way of in order to transmit some information points, let's say from point A to point B, right? The same kind of a concept they have actually used it and implemented using something called as neural network. Okay, so neural network, as I already told you, that neural network is basically the some kind of a in deep learning, whatever model that we are training on the skeleton of neural network, right? Now, before understanding and before diving it into the, let's say, neural network, I just wanted to ask you some question. Okay, I have prepared some kind of a good things for you, right? So let's say that suppose if I wanted to make you good tea, right? Now, what will you do? Like you have a milk, you have a sugar, you have a tea leaves, and you wanted to pass some extra material. You can actually do it by yourself, right? So what will you do? You'll go to the kitchen, like you try to pick up these many things in some X amount, right? And then you are again putting all these things together, and you wait for some time, and then the tea will be prepared and you're offered to serve. Okay, in this way you will be making a good tea. Okay, now in order to decide that whether your tea is actually good or bad, right, other than tasting yourself, what will you do? You will basically go and serve it to the other people in your family, and you wanted to take the reward from it. Okay, and then they will tell you that whether you should add some extra cup of ginger or sugar or milk or something like that. Okay, so in this way you actually learned it by some kind of a simulation technique from the external world, right? And in this way you try to update yourself, and then by the time goes, right, so you started making a good cup of tea, right? Again, so you're actually making a good cup of tea at the very first step. Congratulations. But it generally does not happen, right? So for me, I think it took like 2-3 times in order to get a good feedback from my family that whether I able to make a good cup of tea or not, right? So again, coming to the point, let's say that I have something called as these many amounts that I have actually taken, right? So something in grams, right? And these many things I have actually taken and actually intermixed everything, right, in order to make a tea, right? Now in order to make a t, right, so now these are actually what, these are basically my input, okay, and I actually intermix everything, okay, and I wait for some time, right, and I will get some output, okay, right, and based on this output, right, I need to again change like these kind of amount to make it a good t, right. So this is the entire concept of like how the neural network is actually works, okay, to be very simple, because I don't want it to prolong this lecture for a longer period of time. My intention is to make as easy as possible, make things as easy as possible for you, okay. So what is actually the input neurons? The input neurons is basically your this one, okay, that whatever the set of problem that you're getting, right, so on the set of problem, whatever the inputs that you're actually taking, right, some different inputs that you're actually taking, that is basically like make the problem suffice enough to, you know, get you a good kind of a predictions, right. Now that if you just combine everything, you started making a whole skeleton of neural network, okay, and these are the building blocks. So these are basically the neurons, correct. So let me just, yeah, so these are basically the neurons, right, so these are actually the neurons. In this way you started like making something good, okay, and these are basically the interconnected to each other, right. So it means for now just understand the keyword, okay. So these are what, these are basically my input neurons, correct, right. These are basically my input neurons, and these are actually the hidden state, okay. It is also a neuron. So all set of the small thing that whatever you're seeing, these are basically the neurons, okay, the same neurons that like our brain cell works, right, the same way. These are basically the neurons, and these are, let's say, edges, I would say, right, and these are basically the hidden layers, okay, and hidden layer also contains some kind of a neuron. Again, these are the edges, right, and then these are actually the hidden layer, right, and then this is also a neurons, okay. So in this way the entire skeleton of neural networks work, right. Now let comes to the another topic, which is like back propagation. Now why it is actually important, as I told you that whenever you're actually distributing a cup of tea, right, so let me come back again. As I told you that whenever you're actually distributing some cup of tea to your family member, right, so you will definitely get some kind of a feedback, okay, and the feedback that you're actually supposed to get, right, that feedback you think by yourself, and then you try to increase some kind of a, let's say, the amount of tea, amount of sugar, okay, whether you should add a very less sugar or more sugar, it actually depends, right, in order to make a very suitable cup of tea, right. So in this way, how you actually do that thing, right, so you started like iterating it via reverse direction, which means that whatever the feedback that you're getting, right, whatever the feedback, the output feedback that you're getting, right, you try to like back loop it, okay, and then go to the very forward layer, and you try to increase your weight. When I say increase your weight, it means that increase the weights of the input neurons, okay. These are basically my neurons, correct. And don't worry about it if you're not getting anything now. As the lecture go, you will understand each and everything. This much I can guarantee you, right. So what is actually back propagation? So back propagation is nothing but, if you try to understand more practically, so it is just that you're actually taking the feedback, right, from your, let's say, output network, or whosoever is actually giving you the output, in order to update the weight, so that next time you try to give the output in a more probable manner, right, so that you could able to make a good cup of tea, right. Now let's summarize it into the mathematical form, like how actually the entire mathematics work, okay. And just like stay with me. It's not a very like hard mathematics. I think you could have understand if you like followed me till now. You could have understand everything. Now when it comes to like summarizing it into the mathematical problem, so I have just written three equations, right. The first is basically the z value, okay. Now what is actually the z value? So z value is like I have the weights, okay, and then I have something called as x1, I have a weight 2, I have something called as x2, I have weight 3, I have something called as x3. Now what does that mean? So here x1, x2, x3 are my input thing, like are my input neuron, okay. So let me just do it something like this. Let me use something like this, and let me make the first neural network, okay. This is my first neural network. Now what will happen is that, because suppose that this is your tea, this is your milk, okay, and this is your, let's say, other ingredients, okay, you are actually adding it with some proportion, okay. Let's say that tea, you are actually adding some, let's say, 20 gram of tea, or let's say very little amount of milk, and then let's say some other ingredients which is like represented by weight 3, right. Now if you just try to combine it, it means that you will be getting x1 w1, or let's say x2 w2, or let's say x3 w3, okay. Am I correct? Right. Now this is what, this is basically the combined neuron, okay, which means that if you come to this neuron, right, if you come to this neuron, so what will you do? You try to like do the entire summation of all the proportional input that you have actually taken. Okay, similarly, just the example that I given to make a good tea. Okay, so here this is the part, like you will start making and mixturing everything into a one input neuron. Okay, and this is, let's say that you wanted to represent it using something called as Z. Okay, now what will you do? Now it will go and it will try to like give you some output like the y dash. Okay, y dash, which means that, let's say, prepared tea. Okay, prepared tea, I would say. Okay, now your tea is getting prepared. Now if your tea is getting prepared, now you wanted to test it, right? You wanted to test it. So what will you do? That, let's say that you will go and contact with some experienced person, okay, who is like experienced in making the tea. So simultaneously he will actually started making the tea with you. Okay, and let's say that he started making a tea which is like T1. Okay, T1, right? And this is your tea, right, which is like T1 dash, right? Then you wanted to compare. Okay, you wanted to compare your T with this, with the experienced person T. Okay, similarly, let's say this is actually Y and this is actually Y dash. Okay, so can you write the error term? Can you actually write the error term is Y minus Y dash? Okay, because this is just an absolute difference between a good T and the absolute T, like between a good T and the T that you have actually make in the very first go. Okay, and because of this error or because of this feedback, right, you are supposed to update the weight. That is why I'm telling you, you are supposed to update the weight. Okay, these are actually the weight matrices. So you are supposed to update the weights, weight 1, weight 2, weight 3. Okay, and you try to add some more gram of sugar, some milk, some other ingredients, right, and some garlic and some other things, right, to make a good cup of tea, right? So you will be like start iterating every weight one by one, and then you start getting all these things. I think these things you already know, right, because this is my learning rate, right, and this is basically my error part, right, and this is basically my old weight and the new weight, right? Anyway, I will again like iterate it, like try in the later video, so that you will again get a good glance of it, right? So this way I would say the entire like the architecture of neural networks work, right? And sometimes it is also called as perceptron. When I say perceptron, it means that whenever you have a hidden layer, because I already told you, right, these are basically my hidden layer. Okay, these things are basically my hidden layer. So let's say that if I have, let's say, one hidden layer, what does that mean? Understand the keyword, guys, right? So if I have this hidden layer, so can I say that this is a perceptron? Okay, now suppose that if I have, let's say, more than one hidden layer, right, something like this, right? So let's say that something like this. So suppose if I have a neural network which is like just a input can be anything, right? And then let's say that this is the another layer, this is my another layer, this is my other layer. So this is my hidden layer 1, this is my hidden layer 2, and let's say this is my input layer, right? This is my input layer, and then this is like my output neuron, right? Output neuron. I hope you understood till now. Okay, understood like whatever I told you till now, right? And you started connecting every edges to every node, and you started making a good kind of a paradox. Okay, and you wanted to like named it as multi-level perceptron, or similarly a skeleton of a neural network. Okay, so you can actually write multi-level perceptron, MLP, or simply a neural network. Okay, and suppose if I have only one hidden layer, so I should probably call it as a perceptron, right? Now let's come here, this part. So this will actually give you more glimpse about what is actually the perceptron part, right? So this is basically give you like the more about the perceptron. Okay, so perceptron, as I already told you, that you have an input which is like the x2, which is, you have the x1, then you have some kind of a weight. Okay, and then you actually doing the summation of all this weight, right? And then you wanted to check that whether your output is actually good enough or not. If it is not, then it's supposed to find out the error. Okay, now as you can see that this is actually my function. Now you can definitely ask me that what is this function, right? So as I told you, it can be any function, but here we named it as an activation function, right? So activation function, what does it do? Okay, now just think it more logically and more like in a very understandable manner. So let's say that if I having, again taking a tea example, right? So if I'll be having some kind of a, let's say, tea leaves, right? And let's say if I having some kind of a milk, okay, I'm actually adding it, right? So can I write the equation something like this? Can I write w1x1 and then w2x2, right? And can I pass it into this function? So can I tell you that, can I use the probability function? And when I say probability, you already know that I am talking about sigmoid function, right? Because I need a output threshold, which I wanted to benchmark that whether if it is greater than my output threshold, then it is a good T. If it is not greater than my output threshold, then it is a bad T. Okay, because there has to be some kind of a decision person at the very end of the layer who could basically tell and decide that whether I am actually making a good cup of tea or not, right? So in this way, what I'm supposed to do is that I will be actually using some kind of a softmax function. Okay, as you can see that basically when it comes to softmax function, what is that? Let's say that it has to be some kind of a linear separable line. Okay, and then it would able to classify that whether my data is basically belonging from this direction or that direction, like that side of the line or this side of a line, and based on that it will also able to give me the probability, right? Again, like doing the mathematics of this one. So let's say this is my theta value, right? Theta is basically, let's say, threshold. Okay, so let's say that if my z value is actually greater than, then it is actually belonging to class 1. If it is actually less than, then it is actually belonging to class 0, right? And you can also write this. Now can I also write this, right? Can I also write w1 of x1 and w2 of x2 minus theta? Can I write like this? Correct. Can I also write in a equation of line like this? Agree, right? Now because it is an equation of line, so can I draw the line like this? Because it has actually having a negative slope, right? And because I am able to draw this line, can I say that it is actually mostly working on this linearly separable data? So if my data is actually some kind of a linearly separable, so can I able to like just draw this line and able to like make it correct? So this is the way of like perceptron. Like this is how the perceptron defines, like somebody actually defines the perceptron. Now just think about it, that what should be the limitation. Just think it, just pause the video and just think that what should be the limitation of it. Can I say that a limitation is like I have the data of actually two class, right? Suppose if I have the multiple class, can this one single line is able to like dissect, or can this one single line is able to classify the multiple class? Of course not, right? Because we need more lines, right? So in that case, our single layer perceptron fails. Why? Because as the data representation, as the data started increasing, we need more class. When I say we need more class, which means we need more number of hypotheses, or we need more number of line, right? So of course this single line would not be able to do the good classification, right? So what is the limitation? Can I say that it basically fails, right? It basically fails when I increase the data size, or let's say classification size. Can I say like this? So this is basically the one of the limitation of this single level perceptron. Now we move forward to this multi-level perceptron. Okay, so what is this multi-level perceptron? As I already told you, that in multi-level perceptron you will be having more than one hidden layer. It could be anything. Okay, so again, taking one example, if you wanted to make a good tea or bad tea, so this is your input, and based on that, these are basically your hidden layers. Okay, and these are actually the weight assigned to it, right? And then these are actually the divergence and convergence, right? So these are actually the conserving everything, and then we are actually giving it to some kind of a activation function, and then we are actually getting the output, right? Now let's understand something called as forward propagation in multi-level perceptron, or let's say artificial neural network. Okay, and this is also very easy because you would actually understood it now. Now let's try to like dive it more mathematically, like what does it actually say, right? So when I say that I have the input which is like x1, so can I say that I have the input like whatever the input, right? I have x1, x2, x3. Okay, just understood in this way, that these are the input. Okay, which means that these are the input parameter that I have. Based on that, I wanted to make something called as multi-level perceptron, right? So how do we actually start making? So in layer 0, I will be first assigning these things 1, 2, 3, and don't worry, I will show the implementation of it like along the video. As the video comes to an end, I will show the implementation of each and every part of it. For now, just understood till now, whatever till now I have said. Okay, so these are basically my inputs. My input can be anything. Okay, so let's say here you can actually take the example by yourself. So I'm actually taking the input as x1, x2, and x3. Then what I'm going to do is that I'm actually making the one hidden layer, right? So this is my layer 0, and then this is my layer 1, and then this is my final layer, right? Can I write something like this? Because I need to connect, right? Because it is actually connected graph, right? So I need to connect every weight to this node. So whatever the layer node, right? So this is actually the layer node, the first node of the layer 1. Can I say like this? And this is basically the first node of the layer 0. Can I say like this, right? So can I just attach this first node of the layer 1 to all the node of the previous layer, like this one, this one, this one? Can I attach these things? Agree? Why I wanted to attach? Because this is actually kind of information transmitting. So this neuron has to know that what are the weight actually assigned to this to this neuron, via the output of the previous neuron. That is why this is very a conventional way. Similarly, if I go and just ask you like this, that like in the input neuron 2, whatever the weight that I'm, how many weights that I should get the number of edges, right, pointing to as an input of the second neurons of the first layer. Can I say that it is actually this one, right? Can I say this one? Can I say this one? Right? In this way, you started like fixing your first layer. Okay, so yeah, so you actually build your first neuron. Then at the very final neuron, what will be having? Tell me. So in the final neuron, can I have because the final neuron, these are basically becomes the input. Okay, so for these two neuron, these becomes input. For these layer, this becomes input. For these layer, this becomes input. For these layer, this becomes input, and for these layer, this becomes input. Okay, so these layer is actually having a two input, right? So can I just connect with this in neuron into this neuron, right? And this is how like our brain cell also kind of works, right? It works more vaguely, right? Because each and every neuron has to surpass the information, right? And because each and every neuron has to surpass the information, it means that each and every neuron has to be kind of fully connected, right? If I am just talking about this neuron, so this neuron has to be fully connected to the other two neuron. Okay, similarly something like this, right? So in this way, these are actually the weight. And can I say that these are actually the weight W11 of first layer, W11, W of 1 2, and then W of 2 1, and then W of 2 2, right? And then W of 3 1, and then W of 3 2. It means that W of 3 1, which means that the W3 of the layer 0 is actually like going as an input of the first neuron of the layer 1, right? Now let's try to represent it in a matrix format. So can I write something like this? Can I write the input as x1, x2, and x3? Can I write it? Can I write? Yes or no? Right? So let me use some other color. Right? Can I write the input like this? These are my actually the input, right? And can I write the, let's say, the weight matrices? Suppose if I ask you to, can you just represent the weight, all the weight matrices that you actually verbally tell it in the previous in the previous neuron? Can you just try to represent it into the matrix representation form? Can I actually write it, right? So these are my basically the first row, right? So the first row is basically the weight of W11 and then weight of W12, which means W11 and W12, right? So these are basically the layer 1. So in my layer 1, what will be my weight, right? So my weight will be something like this, that these are my W11 and then these are my W12. Okay, similarly for let's say for second layer, right? So for second layer, so I'm actually getting from the second node to the first neuron, right? So just try to understand that these are basically my first node, right? So first node, I'm actually getting it from the first node. I'm getting it from the previous neuron as this one, and this one, right? Like this one, and then this one, correct? Right? Similarly, if I just understood about this one, so I'm actually getting it from this one, then this one, and then this one, correct? Right? And because it is actually having a two node, right? So that is why I have a column 1 and column 2, because it is actually representing the number of nodes you have, right? So can I also represent something like this? And these are basically the bias, right? So bias is something called as the extra node. So let's say that W1x1 plus W2x2 plus W3x3, and then something called as bias, right? That is why it started representing a single form of equation. That's why, right? So because it has two input, it means that it has two bias, B1 and then B2, right? So it is basically like the biases, right? So it is basically two column, right? And can I combine the matrix like this, right? Can I combine the matrix like this, right? Now after doing the combination, can I also like segregate the weight part? Like for example, let's say that can I just after combining, let's say that I wanted to like add it to the bias model, right? Can I actually write it like this, right? Because these are my basically my input 1 and these are basically my input 2, right? I'm doing nothing, right? So I'm just actually like adding it, right? So can I just from W11, so let's say that it is basically, so it's basically like W11, right? So it's this row is actually having, let's say the first row, and basically it has actually 3 column, right? The first row it has actually 3 column, and then let's say the second row is also actually having a 3 column. So can I just add column wise to this one, B1, then B21, then B31? Can I add like this? Can I add this one with this column, right? So yeah, can I actually write something like this? Okay, and if you're actually wondering about that, how it is like how it is actually adding, because these two are the different kind of a dimension, nothing, you can just take the transpose of it, right? You can just take the transpose of it so that it becomes the same kind of a dimension. Okay, so 2 cross 3, it is also, by taking the transpose, it will also become 2 cross 3. Okay, and then you would actually probably end up with this kind of equation, right? And bias is like almost like tending to 0, right? So can I also make this as a 0? So these things become 0, and then these things become also 0, right? So these are basically my final input, right? So these are basically my final input. Now let's come to this part. Okay, so these are basically the summation value, as you can see that thing, right? Let me, yeah, so these are basically the summation value. These are basically the summation value. Now what is the value of this one? So this is actually the output of the first layer, right? Because these kind of the entire handling, right? So this is actually happening in these two layer. Okay, which means that the summation at the layer 1 of the first neuron is actually like happening here, like the computation start happening in this neuron, right? So what would be the computation? Again, let's iterate it one more time. Okay, so the computation, can I write the computation like this, which means that x1 and then w11 of 1, right? And then can I write the x2 and then w21 and then 1, and can I write x3 and then let's say w31 and then 1, and can I just write at b1, right? If I just making it b is actually equal to 0. So this is basically the output of this neuron. Okay, the output of this neuron, if I say the output of this neuron, which is like 1. So can I just write output of, let's say, neural network 1 of layer 1, right? So can I just write like this, right? Can I just write it like x1 w11 of 1 plus x2 w21 of 1 plus x3 w31 of 1, right? So this is basically my output. Okay, right? Now similarly, if I ask you to, like, can you also write like this? Just pause the video and write it by yourself, right? So can I also write for the second video, can I also input, can I also write like something like this? Correct. Now here there is something called as activation function. Now this I wanted to tell you, right? So now at every hidden layer, right? So whatever the summation that you're actually doing, right? Now once you do all these summation, right? So that summation itself has to pass to some kind of a function. Okay, because the function is actually necessary. Why? Just think about it. Because if you're not using the function, it means that all this neuron is basically converged to a one single neuron. Okay, so there is no purpose of then using the multi-layer perceptron. That is why I am actually using the activation function, right? So again, if someone asks you that why to use the activation function at the very hidden layer, just tell them that if we are not using the activation function, it means that all the neurons are basically converged into the one single neuron. Okay, so that is why. So can I just give the output of these things into the activation layer? So activation also performs in this layer only. Okay, so let's say that this layer 1 is actually having activation, some kind of activation function, and then this layer 2 is also having some kind of activation function, right? So this is the output of my layer 1, and this is the output of my layer 2, right? So sorry, this is the output of my layer 1, and this is also the output of my layer 1. So this is the output of my layer 1 of neuron 1, right? And this is the output of my layer 1 of neuron 2, right? And this actually has to go as an input to the activation function. So can I write as an input to the activation function? Can I write like this, right? Can I write like this, the activation function? These are the AF activation function. So can I pass this as an input? And which kind of function I am actually using? I am actually using the sigmoid function. Okay, and I will also tell you that when to use which kind of activation function. I will also tell you the types of activation function which is like mostly used in the neural network creation, right? So this is basically the input of the second layer. Now please understand that this is actually the input of the second layer. Now what is the input of the second layer, right? So this is basically the input of the second layer, because this is my layer 1, so this is my layer 2, right? So these things is actually like can be considered as an input of layer 2, right? So now these things is basically the input of layer 2, and similarly like reiterate the same process again and again, right? So again, these had some weights. Let's say this will be having some weights, this will be having some weights, right? And the final output of neuron 1s, right? Just understand what is the final output of neuron 1s. Can I say that the final output of neuron 1 would be the activation function of the summation equation, right? Similarly, for neuron 2, it is actually the activation function of the summation equation, whatever summation equation that you get, right? You wanted to pass it into the activation function, right? So can I just name it as some other name, right? Some other, so you can actually write, like, name it some other thing, right? So can I also name it like x1 and x2? Now this x1 and x2 is now become the another set of input neuron for which layer? For layer 2, this one, right? And then similarly same thing. So you basically like converge the entire thing, right? You basically like converge this thing, the entire thing into this one, right? I hope it clears, right? You, and then for the last layer actually you're doing this, and then again the weights, right? And again you wanted to do the summation, right? Again you wanted to do the summation, let's say x1, and then let's say w11 of layer 2, and then let's say x2, and then w2 of 1 of layer 2, right? And these are basic, and then some bias, so bias is actually equals to 0, right? So this is your final summation equation, and this also has to pass to the some kind of activation function. The same thing I'm actually doing here, okay? So whatever the activation function of the previous layer, I'm actually passing it here. I'm actually like multiplying with them w11 and w12, which is like this one and this one, right? And then I'm able to like construct, or I should say decompress everything into a one single activation function, right? So this has to be my final output, right? Because see, this is me the activation function of the previous neuron, and then I'm actually adding with some kind of a weight. This is the like the output of the previous neuron, which is now become the input of the last neuron, and then I'm actually adding it with the weight, okay? And this is basically the bias. So bias, I'm actually like making it 0. So can I just again write the activation function something like this, right? So basically from this, what have you understood? You have understood that the neural network is nothing but it is just a some set of chain of activation function, right? Where you will be having some kind of an input which is connected to some kind of a hidden layer, and then this hidden layer, for each neuron you will be having some kind of a summation value has to pass into some activation function. Similarly for this one, it has some summation value, so it has to some pass of activation function. Similarly activation function of summation value, and again these things can be converged and can be write is 1 2 3 this one, right? Can I write this one? Are you getting it, right? Now let's say again you try to approach this kind of equation, then can you just converge it into this one, right? Now this becomes your input, right? And can you just converge it into one single output? Now this is basically output neuron, right? So what I'm doing, I'm just like doing the like compressing it, like the compressing the first layer into a activation function, okay? So that this is actually became the input to the next layer, okay? And again whatever the output of the next layer, I'm actually compressing into the activation function, okay? So that this becomes input to the next layer, okay? And similarly this is actually my final output, right? So this is nothing but neural network is nothing but the chain of activation function, just understand this, right? And actually you can also try it by yourself. So let's say that for now I have actually taken the three neurons, right? Just try it with 4 neurons, okay? I'll give you one task, okay? Just use this one, x1 x2 x3 x4, right? 1 2 3 1 2 1, okay? What I want is that, let's say these are the weight, right? You can actually assign the weight by yourself. I'm just connecting it, right? And this is basically fully connected. Similarly this similarly this one, right? What I want is that I want you to first create a weight matrix, okay? Then I want you to create a weight matrix. Now I want to use the weight matrix into the activation function, okay? And just go series by series, okay? Now what will you do? First of all, let's say this is my layer 0, this is my layer 1, this is my layer 2, and this is my final layer, okay? So what would be the output of first layer? Can I say that it is actually the summation of all the input to the weight, right? And again it is actually passing it into the activation function. Similarly, can I say that these are actually the input of all the weight, and can I also pass it into some kind of activation function? Similarly activation function. Now these things are basically compress it into, so instead of writing these two, can I write 1 2 3 1 2 1? Can I write something like this? This is nothing but it's just activation function, or let's say the input of this neuron, which is, let's say, input of layer 2, right? So can I write it as again x1 x2 x3 or some other input, right? So again just do this, right? So can I just write it as, for this neuron, it is nothing but it is just the activation function of the previous summation, like the previous summation of these three neurons, right? Similarly for this one, can I write the previous summation of these three neurons, right? Something like this, right? I hope you're getting it, right? I'm just reiterating again. So these two are actually converged into this, again, this neuron, and this is basically the activation function, or let's say the activation function of the previous summation. That this is basically the activation function of the previous summation, and this again I am actually passing it, right? And this is actually my final activation function. Activation function, right? Or let's say final output, right? So this way you will be start like making the neural network by yourself, right? So I just wanted to like, so it's your task first, again, recreate the matrix by yourself, okay? Do the matrix joining operation and everything, and at final just let me know that which kind of activation function are you using, and what is the final output you get, okay? So then we will again, like in the next upcoming video, we will again brushing up some concept, okay? I'll tell you about each and everything in detail once again, so that you will get the conceptual understanding of it, okay? Thank you. Okay, so let's brush up again the concept that we have done before, okay, so that it will give you a little more clear intuition about whatever till now whatever we have done, right? So again, we have done about, like, we have taken something as a definition of neurons, okay, that what is basically a neurons, what is the input of the neuron, what is the output of the neuron. We have taken the example of T, the other ingredients, and some like another like input, and then try to define it as an input with some weight matrices, okay, and then giving it some this neuron where like the magic happens, right? And if you just wanted to like look into the more magnified way of like whatever which is happening inside this neuron, so you can actually look it like this one. So every neuron is basically contains what, okay? So every neuron contains one activation function. So here you agree with me, right? The other way is that every neuron is also contains some summation, okay? So whatever the neuron that is actually taking it from the previous inputs, okay, it will try to do the summation operation over it, right? And then there is something called as bias, okay? So that you will pass the output, like the combination of these two, into a activation function, okay? Now there are many type of activation function, I will discuss it later, right? Now here I've just written the type of activation function, which is like ReLU, TANH, sigmoid, softmax. I'll tell you that according to problem by problem which kind of activation function tackles what, okay, and when to use what, because in practical scenario it is very important, right? And again, these are actually the output, okay? So these are basically the input neuron, and these are actually the weight assigned to it, okay? And these are actually the weight assigned to it, and this is by each neuron, okay? And each neuron contains the structure like this, right? And this is basically the summation value. Right? And then it is actually passing it as an input into the activation function. Again, we do the summation, and then we pass it into the activation function, and we get something like this. Now this becomes the input, okay? This becomes the new input to the set of neurons which is present in the next layer, okay? So again, if you wanted to find out, like, so last lecture I asked you to like perform the weight matrices, okay? So the weight matrices will look something like this, right? So this is my weight matrices, so that from all the previous neuron, okay? And there are two ways to look into the neuron, as I already told you. The first is the expressive function, okay, which means a set of, let's say, a pipeline of activation function. The second is like feature transformation. Now when I say about feature transformation, what does that mean? It means that you have an input, and your input is very limited, but you wanted to like visualize it, maximize your input, right? So you try to like use it by increasing the set of neurons, right? Similarly, just understand in this way, right? Suppose that if I ask you that do the multiple of, let's say, 2 cross 6, right? So we all know that it is actually 12, right? So how our brain is actually processing it, when I actually give you a number, right? And when I say you the multiplication, so the number and multiplication has given to your memory feed, okay? And inside it is actually like connecting with all the neurons, right? Whatever the things that you have learned how to multiply it, right, from your kindergarten, right? How do you actually multiply it and everything, right? So it is basically connecting to all the input neuron, which is basically necessary. Similarly in this way, right? So you have some kind of a feature input, right? And if you wanted to like look it and in a more dimensionify manner, you can actually like try to increase the neurons, okay, in the second layer, okay? So here the compression and decompression happens, right? Now again, let's come to back propagation. So what is basically back propagation? Back propagation is basically a way, okay, in order to update your weight, right? So yeah, so suppose again taking the same example, so let's say that this is my milk, this is tea, and then this is the ingredient I have, right? And then these are the summation matrices I will be making. Okay, I will be making these kind of a summation matrices. This is basically my summation matrices, and this is the output function, right? So activation function, right? So these matrices has to go into this one, into the activation function. Okay, so let's say that I am actually using the activation function as a sigmoid. Okay, so in sigmoid activation function, I have some, like the graph I've already told you before, right? So I have something like this, right? So I have something like, let's say that in sigmoid activation I have something like this, where I have some threshold, okay, right? And then if it is actually like going above the threshold, my like already set threshold, if it is going above, then it is belonging to the class A, otherwise in class B. Similarly, let's say that it is like giving you below the threshold, which means that it is like only 30% you are getting a score, that so it is a very bad T, right? You are not even passed the test, right? So how will you do? So you will again update the weight matrices, because you will not going to update the x1, x2 and x2, because these are already preset input you have. Okay, which means that I have already given you the ingredient, I have already given you the milk, the sugar and the other ingredient, right? I'm not supposed to give the other extra ingredient as well, right? You need to just update the weight of that ingredient in order to make a good cup of tea. Okay, so you need to update the weight parameter, right? Just like we did, like we used to do it in the ML foundation. Like if we going to see the any machine learning model, there is actually the weight assigned to it, right? Similarly here also there is a weight assigned to it, so we need to update the weight. Now here, update the param, but like for example, let's say that if you wanted to update the weight, right? So how does the weight updation happen? Okay, so can you recall, as I told you in the very early part of the lecture in ML foundational course, which is like the new update weight is basically the old update weight minus of some learning rate, right? And some kind of a gradient loss, where I already told you the gradient, what is gradient before. Okay, so now can I just write it, the gradient equation, something like this now. Okay, so now let's say that we have a multi-layer perceptron. Okay, and this is just a single layer perceptron. Let's say that we have a multi-layer perceptron. So we have something called a layer 0, layer 1, layer 2 and layer 3. So can I just represent this as this one? Can I represent this as this activation function, right? And can I just write it as this equation, like this is the input of my layer 1, right? Similarly for layer 2, can I just write it as this one? So this is basically the input of my layer 2, right? So this is basically the input of my final layer, right? And then in the final layer, I'm supposed to like organize everything and write it into this format, right? I hope you get it, right? And now wrapping all these concepts, so can I just write my final output as something like this? So where my final output is just an activation function of the third layer. Okay, so whatever the output that I get it from here, okay, this is my actually the final output, correct? This is basically my final output. Now this output, if you wanted to unchain it, right? Because I already told you that in order to update the weight, right? In order to update the weight, first of all, you need to find out the gradient. Without gradient, you cannot even update the weight, right? And what is gradient? Gradient I already told you before, right? It is just a differential way of your loss function. Okay. Now just unchain it. Okay. So can I write this activation function after unchaining? Can I write something like this? Okay, because this activation function is just at layer 3 is basically the activation function of layer 2, correct? And layer 2 is basically the activation function of layer 1, correct? So can I write something like this? So this has to be my final output if I basically try to unchain it, right? This would be my final output. Now this is your y hat, right? And you have your y is basically your actual, okay, and this is basically the y hat. So you wanted to find out the loss function, right? And how will you actually find out the loss function? It depends, right? Like for example, if you have a classification set of a problem, you have another kind of a loss function where you have a cross entropy loss, you have a probabilistic loss, you have a hinge loss, and you have a other kind of a loss as well, right? You have a binary cross entropy loss. If it is a regression problem, then you will be having another set of loss where you will be having a MAE, mean absolute error, mean squared error, right? So these things I already told you, like what are the loss function. So so in order to like find out the gradient, right? So can I just write it into the some kind of a gradient equation, something like this. Let me use it some other color, right? So can I write my gradient equation something like this, which is like the output, this is my final output, right? And final output from where I'm actually taking this is my final output. This is, if I just unchain it, right? If I just unchain this part, the output of final layer, okay, if I unchain it, I will be getting these many big equation, right? And now I am just passing this equation into my gradient function as an input, okay, and I'm actually taking the differential part of it. Now if you could just visualize, then if you're actually like finding out the differential, right? So can I say that you need to process it backwards, because this is actually like depending upon this one, this is depending upon this one, this is depending upon this one, right? So can I just write it like this one, this is the output parameter, and then like again multiplying partial differentiation with the inner parameter, again multiplying the partial differentiation with the more inner parameter till it reaches the first layer, right? Now this is the process which we call the chain rule, okay, because actually we are unchaining the operation, right? We are actually propagating it back in a backward direction. We are actually propagating it in the backward direction. Why? Because we wanted to find out the gradient function. Why? Because we wanted to find out, like, because we wanted to update our weight. Again, in order to update the weight, you need to find out the gradient function. In order to update, like, in order to find out the gradient function, you need to do the back propagation. In order to do the back propagation, you need to find out the loss. And in order to find out the loss, you need to just map it, that whether which type of loss function that I'm using, right? I hope you get it. Now let's understand about the type of activation function we generally used and we practice while training the neural network. Okay, so till now, whatever the things that you have understood, it's basically the building block of the neural network, right? Now I have told you that I will be using the activation function, right? But what are the types of activation function which is like generally using in most of the industrial specific data set? Okay, so let me just hop into that thing. Okay, so see, my main motive is that I will be taking barely like very little time of yours. Okay, that is why I am preparing the notes by myself, right? So that you don't need to prepare anything. Okay, I'm just giving you a very crisp understanding of each and everything. Okay, so whatever the things that till now I have covered, it's basically the conceptual understanding of the deep learning, right? Because that is our course is basically more concentric on, right? So let's understand about the what is the kind of activation function, right? So as you have understood, like the neural network is nothing but it is just a set of activation function or the chain of activation function at the end, right? So yeah, so it is just nothing, it is just like this, right? So it basically like it, just remember that the neural network at the end is basically a huge function, right? It's basically a huge function which contain, right, which contains all the information, right? In the activation function you will be having the summation of weights, the weights parameter, the biases, and other things as well, right? Now let's understand about like what are the types of activation function, right? So as you would already understood that we have some kind of a sigmoid activation function, which is nothing but treat it as a function. Okay, just remove the activation till now. Okay, treat it as a function. So its sigmoid is just a function, and the graph of sigmoid is something looks like this, right? Where you have some threshold. Okay, so if something is actually beyond this threshold, it means that it is belonging to the some other class. If it is belonging to the below this threshold, it is belonging to some alternative class, right? And this is basically the equation of this sigmoid function, right? And what is the advantage? So advantage is like it is basically 0 to 1. That is why it is most suitable for any of those problem which is like very needful to get the output in a very probabilistic manner. That is why in most of the cases we used sigmoid or softmax function. Sigmoid for multi-level classification, softmax sigmoid for binary level classification, and softmax for multi-level classification, right? So as you could see that what is this equation? Just assume that this equation is basically your final output. Okay, this is basically your final output, because I already told you in the back propagation lecture as well, right? That this would be the final output that you will be getting at the very end, right? So in order to update the weight, what you need to do? You need to do the back propagation, which means that you need to first find out the gradient. Okay, and in order to find out the gradient, you need to find out the final equation. You need to find out the loss function of it, right? And now you are taking the differential form of this one. So writing it into a differential form will be another complex equation. Then you do the back propagation part, and you know the whole story, right? Now when I say, right, so it is not that every time, like only a single time I need to update the weight. Correct, I need to update the weight every single time. Let's say if I'm running the model for 50 epoch, right, 50, it means that for 50 epoch I need to update the weight, right? Now there is actually a one limitation of using this sigmoid activation function. Okay, because let's say that if I'm updating the weight and I keep on updating the weight, right, there will be a point where like my this differential part actually becomes zero, right? There will be a point where like differential part is actually becomes zero because I keep on updating the weight, right? Now what will happen with this? It will happen that after this there will be a no longer updation to this weight. Okay, that is why we need to use early stopping. I will tell you later, like when and like where to use early stopping, right? For now, just understood that whenever you are actually updating the weight, right, epoch per epoch, right, while training, right, so there will be a point come where at the very suitable point, this differential equation, like this tangent itself is getting zero, okay, which leads to the weight updation equals to null, okay, because the weight cannot be updated later on, right? So that is the problem that many people can ask, that what is that problem. So this is basically a vanishing gradient problem, where like the gradient, okay, the gradient means what? The gradient means your differential equation, so it is completely vanished. So it means that the weight, the next time the weight, whatever the weight will get update, right, so it will no longer have the significance of this weight updation, right? So that's why. Similarly, let's say that you have a tan-h activation function, right? So what does this tan-h will do? Okay, so the graph of tan-h will look something like this. So it has something called as, so ranges from -1 to 1. Okay, now just understood this part, and this is very interesting, right? So if I take you to the condition where, let's say, you have a something sigmoid activation function and you have a tan-h activation function, right? Now you are using, let's say, first model you are actually using the sigmoid activation function. In the second model you are actually using the tan-h activation function. Now just pause this video and just think that which one you would feel that the weight updation will be much faster. Okay, so I hope you understood, right? The weight updation will be much faster. Which one would you think? Okay, most of you come up with the equation that the weight updation will be the tan h, and you are actually right. Why? Because if you take the differential of tan h, right, and if you take the differential range of tan h comparing with the differential range of softmax, right, so the differential range of tan x is actually greater than the differential range of softmax function, right, leading to my weight updation. So suppose that this parameter is basically higher. The more higher this parameter is, which means the more higher the differential equation is, right, the faster I will be updating the weight. Got it, right? So in tan h and softmax, which differential equation has the range is maximum, right? So tan h is actually, so let's say that the range of tan h differential equation, right? So it is actually greater than the range of softmax or the range of sigmoid. Okay, the range of sigmoid. That is why the tan-h activation function, the weight updation using the tan-h activation function is much more faster. Okay. Now again, it will also like, yeah, so this one, see, the derivative of tan-h is basically like the greater than the derivative of sigmoid, which makes the weight faster. Okay, so it is basically converging faster, right? But again, it has a problem of vanishing gradient problem. Why? Because again, so there will be a point come where, let's say, because there is no narrow point, right? So that is why it is like kind of a curve. Okay, so there will be a point come where like your weight is completely lying into this area. Okay, which means that like your differential equation, your updated differential equation will be lying under this area, which means that your weight, the next weight updation will be zero. Okay, so that is why it leads to problem of vanishing gradient problem, right? Then the most frequently used the activation function, which has been using, like, which a lot of practitioners and researchers are actually using in the middle of the hidden layer, which is like the ReLU activation function. Okay, why ReLU activation function? Let's see the graph. So see, if you can see the graph, right, so at the all the negative part it is actually making zero, and all the positive part is actually exponentially increasing, right? So if you see the equation like this, right, it basically solves the gradient problem, right, because it has a like very top edge, something like this, right? So that is why it basically solve the gradient problem, vanishing gradient problem, right? And in image generation, like the image input neuron, whatever the neuron that you're getting, right, and suppose if the weight is actually negative, right, so you basically use the ReLU activation function, so that you wanted to like counter the dead neuron, right? So that is why it has actually a dead neuron problem faced by ReLU, right? Again, ReLU is actually faster training than tan-h and activation function. It means that the differential range of the ReLU is greater than the differential range of tan-h, is greater than the differential range of sigmoid. That is why ReLU also converges very faster. That is the reason that we are actually using ReLU activation function in the middle of hidden layer. Again, leaky ReLU, again, what is the disadvantage of ReLU? That we have a dead neuron problem. I don't want that neuron to be zero. I want neuron to be some kind of a like very minimal weight. Okay, that is why I'm just like giving these gap. Okay, so that is why it is called leaky ReLU. Similarly, when it comes to softmax activation function, it's very easy, right? Softmax, which means that whenever you are actually encountering the problem which needed to be like a multi-level classification, then you basically try to go with the softmax activation function, right? So the equation of softmax something looks like this, right? And you will be getting the softness activation function. So basically, you use the softness activation function often at the very end of the neural network. Okay, end of the neural network layer, the final output layer, right? Similarly, you will be having a switch. You will be having something like switch is also, but it is very least used activation function. You can actually see the graph. Okay, so it actually depends upon like what kind of a problem curve you have. Okay, what kind of a like details you have about your problem. Based on that, you're supposed to use the switch activation function, right? So yes, so that's it. Like suppose like which activation function shall be used, different task. Again, whenever you have a regression problem, you should use the ReLU activation function, right? Whenever you have a two classification problem, you should use the softmax activation function, correct? Now whenever like let's say a tanh activation function, softmax, sigmoid, these things, right? And multiple class. So for if it is a multiple class, you are supposed to use the softmax. So again, if you have a regression problem, just go with the ReLU, tanh, softmax, or let's say sigmoid, right? And whenever you have a classification problem, and if it is a two class classification problem, then go with this tanh or let's say the sigmoid. And if it is a multiple class classification problem, then go with the softmax, right? So I hope you get it. The activation, like the types of activation function that we are supposed to use into the neural network. Now let's see about the another very interesting and crucial topic of using the dropouts and batch normalization, right? So like why we are actually using the dropouts and batch normalization in the middle of hidden layer is that to avoid the risk of overfitting and to make the process more smooth and more static. Okay, or to make the neural network conversions more faster, right? So when it comes to dropout, now what happens in a dropout is that whatever the neural network that you have, right? So when it comes to overfitting, it means that it is actually like gathering all set of data points, okay, which we don't want, okay. So what we actually needed and what is very crucial is that why not we just deactivate some of those neurons, okay, so that the information that it is feeding to the next hidden layer, okay, it is not the complete full information, it's the some percentage of the information. And why we are actually intending to do it, because we don't want to overfit the data, that's why. So in order to understand a dropout, we can actually like handle the dropout to so the risk of overfitting. So in order to like handle that point, so you need to like use the dropout in the middle of the layer, okay. So there are two way of looking at the dropout, like the regularization. The first way is that using the regularization, okay. So there are two ways to look the overfitting. The first way is that you can either reduce it using the regularization term, where you have a L1, you have a L2, okay. Then you have a ridge, which is like the combination of the L1 and L2. Elastic net, right, which is a combination of L1 and L2. There is a lasso, there is a ridge regression and other things. You can actually like use it into the regularization term. The other thing which is like most commonly practiced when it comes to deep learning in neural network in the middle of the hidden layer is that you use the dropout, okay. So what is dropout? The name suggests that whatever the inputs layer, that whatever the inputs you have, right, so this is basically your first layer, okay, and these are basically the hidden layer, right. So you basically deactivate some of those hidden layer neurons, okay. There is something called as percentage ratio or part to percentage ratio. Let's say that if I keep the probability as 0.6, it means that I want to like deactivate the 60% of the neuron, okay. So if I just in the hidden layer 2, if I just put the dropout ratio as 0.3, it means that I want to deactivate 30% of the neurons, okay. And always make sure that you don't do dropout at the very early stage of the input layer, okay. Why? Because you really don't want to like manipulate your input layer, okay. Because if the input itself is like giving it to the hidden layer, okay. If you're actually like masking the input itself, then it is not a very healthy practices, because you are making this model to forget your information at the very first layer, which you don't want, okay. The purpose of using the dropout is to reduce the overfitting, right? Not with the intention that you should always like use the dropout at the very early layer so that your data itself is getting compromised. That is why, right? So I hope you get it from the dropout, right? So why we are actually using the dropout, so that we can actually like reduce, or we can actually like switch off some of those neurons, okay, in the hidden layer, so that it will not overfit, okay, so that it can actually take your data and like proceed it in a more manual and smoother way, right? Now the other thing which is like which is very common is batch normalization, right? So the batch normalization, what does that mean is that But before, like, please try to understand that batch normalization, that most of the people confuses, that the batch normalization normalizes the weight before giving it to the new layer. Okay, it does not normalize the weight. Okay, it actually normalizes the activation function. Okay, the things here actually like giving it to the activation function. I told you earlier, right? So every neuron will be having some kind of a summation, some bias, and some activation function. Okay, so whatever the weights that that this neuron is getting, okay, batch normalization does not like normalize this weight. Okay, after the activation function and before giving it to the next neuron, okay, it actually normalizes the set of activation function results that you have. Okay, so this should be the flow. Okay, that this is actually your input, this is actually your input, this is your layer, hidden layer, which means that which is your linear layer, and this is your, we are actually supposed to do the batch normalization, okay, over this summation part, and then you are supposed to give it into activation function, and then it will proceed to the next layer. Okay, I hope you get the flow. So batch normalization, like in the modern scenario, so if you really wanted to interested in this equation, you can actually like understand that this is actually the mean, this is actually the normalization formula. Okay, and this is like the scaling factor, right? So where like the gamma and beta are like the trainable parameters. So whenever you're actually like training into the backward back propagation, so you can actually like try to train this parameter as well, so that next time it does the normalization more perfectly. Okay, so that all the parameter actually align towards the mean. Okay, and then let's say that it has a very good standard deviation. Okay, that's fine. So again, the modern days alternative of batch normalization. So in most of the times we go for this batch normalization, but these days I think the many researchers are actually using the layer normalization, group normalization. You can try it by yourself and like see the result, that how is going to impact your result, right? Then the Evo normalization, the instance, and then the like the synchronous batch normalization. So you can actually try it out. Okay, and don't worry, like these things are actually like, it's very common term to use. Okay, and you can actually like use the batch normalization from the TensorFlow library as well, right? So from TensorFlow keras, if you go with the sequential, you can actually like other than like making the neural network, you can actually attach the dropouts in the middle and the batch normalization. Okay, so these things are already supposed to be present in the pre-built library, so you don't need to write a very complex equations. Just understand the concept of the dropout and the batch normalization. Okay, so why batch normalization? Because we wanted to so in the neural network, you wanted to like make your flow convergence flow more effectively. That is why you're supposed to use the batch normalization. And why dropouts? Because you wanted to reduce the failure of overfitting. Okay, so it has a two-way. Either you go with the regularization term, either you use the dropout term, or you can actually go with both. Okay, so these things just keep in mind, the dropouts and the batch normalization. That's it. Thank you. Okay, now, so I think this is supposed to be a very last video of the neural network architecture before we go for the convolution neural network part, right? So in this lecture, we will be covering up with the few keywords, and which is like very necessary and mandatory keywords for any like deep learning practitioners, I would say, right? So in this lecture, like we are supposed to understand about something called as dropout. Okay, then we are supposed to understand about the optimizer part. Then we are supposed to like understand about what is batch normalization, and then again at the finally we come up and conclude with the what kind of loss function that anyone should supposed to use, right? So as you can see that this is basically the optimizer, and this is like very interesting, a very interesting video this is supposed to be, because here you will be understanding about this optimizer part, right? Now, just let me tell you, right, that whatever the weight updation that we used to do it before, right, we what we are doing is that we are just conventionally following the W new is equals to W old minus of some learning rate and some gradient, and some, let's say, gradient, right? The differential of the gradient part, right? Now it is always not necessary that you are supposed to use this weight equation, right? You can use other weight equation as well. It's actually depend upon you that what kind of a equation that you are using it to update your weight. Okay, and that is why here the optimizer come. Okay, so optimizer, like, so again, like I'll go with one more time. So till now, whatever we have understood about the back propagation part, right? We need to update the weight, right? In order to update the weight, you need to compute the loss. You need to find out the differential equation in order to compute the loss, and then you are actually updating the weight, right? And this is like not a very single golden rule for a weight updation. Okay, there are other optimizers as well, and which is like more practical, because like a lot of industries are actually using these kind of an optimizer in order to build and train the model, right? So as you can see, right, that when and where you should use these kind of optimizer. So again, there are many kind of optimizer. There is a SGD, which is like stochastic gradient descent optimizer, right? Then there is something called as batch optimizer, okay, batch gradient descent optimizer, or let's say BGD, right? Then let's say you have an Adam optimizer, like which is like mostly used in all those terms, okay. And don't worry about all these things, because like the TensorFlow, the libraries that which I'm supposed to implement everything, right, this contain all this. We just need to like import the module and everything, our part is getting done, okay. So don't worry about like whatever the complex equation that you are seeing it now, okay. You will get everything handheld practice of entire thing in a very detailed manner, okay, when I come to the implementation part, right? So yeah, so these kind, and then let's say the another kind of activation function like RMS prop, right? And there's so many activation function. Like even you as a creator, you yourself come up with a lot of activation function whenever you wanted to do a research in like the deep learning part, right? So again, so this table is very important. You can take actually the screenshot of it, okay, and then you can actually use it, okay. So let's say that you're actually training a ResNet or some ImageNet model, right? So this is like the variants of convolution neural network. I will tell it in my like next lecture. So this is like the recommended optimizer is SGD, and the momentum, like the momentum optimizer, right? Then this has to be some learning rate, this one. And then for many vision level tasks, you're supposed to use this SGD optimizer, stochastic gradient descent, right? Now suppose that if actually training some kind of a vision encoder, some swing. So swing is basically a type of a variant of transformer model, okay. And let's say that if you're actually using the convolution neural net, right, then you are supposed to use some kind of a Adam weight, like the Adam optimizer, okay. Similarly, if you are actually fine tuning any BERT model, okay, or robot model, or like these are basically the variant of your transformer model, right? Again, you are supposed to use the Adam optimizer, right? Then again, from scratch, if you're making a LLM like for training, then you're actually supposed to use Adam or Lion optimizer, right? Then and like in most of the Kaggle competition, like people are supposed to use either SGD, Adam W, or let's say the momentum optimizer, right? So momentum is like basically like it actually works on this something called as there is a running delay, right? Or let's say the running averages, okay. So if you just wanted to like deep dive into this, just let me know so that I can also cover this running averages concept, okay. And then let's say RNN. So RNN is basically a kind of a sequential way of like understanding the time series model, or let's say you wanted to generate a next form of word, right? And you have a, let's say, sequential way of output, right? So the next output, you're supposed to use some kind of a recurrent neural network, right? And LSTM and some other variant of it, okay. So there actually RMS prom is mostly used, okay. It is not a one single generic way that you're supposed to like unilaterally choose this kind of like optimizer function. You may like try to use different optimizer function in order to know that how it actually works, okay. So these things. So again, like coming up with the flow, okay, I hope you'll get it right. So let's say that coming up with the flow, what will happen is that let's say that I have an input model, okay. Let's say that I have x1, x2, x3 and x4. These are my inputs, and let's say these are my hidden layers, okay. And this is some kind of a output layer that I will be getting, okay. From this I will create a loss, okay, which means that I will be doing the back propagation, right? And in order to do the back propagation, I need to find out the gradient. So in order to find out the gradient, right, so like I need to first write the loss equation, right? Write the loss equation, right? And in order to write the loss equation, after that I am supposed to go and weight updation, right? Weight updation, right? Now when it comes to weight updation part, right, so before weight updation there is one more thing which is like optimizer, okay. So here in this pipeline the optimizer use in this here, okay. So this is basically the optimizer, so that that whatever the weights that you are actually like upgrading, right, so you're not like singularly following the one equation. You can actually follow more than one different equation for different problem statement, right? So yes, now let's understand about this last topic, okay, of the entire like neural network coverage. The first is like loss function, okay, that when and where you are supposed to use the loss function. Again, whenever you have a regression problem, you're supposed to use, let's say, MAE, MSE, like mean absolute error, mean squared error, okay. Mean squared error, which means that if you have some kind of a outlier, right, you're not supposed to use the mean squared error, because squaring it will going to enhance, let's say, loss pretty much higher, okay. You don't want that. That is why you want, so if like the data, if you're not clean the data and the data is basically like contain outlier, you basically go with the MAE, right? Similarly, MSE, if your data does not contain any outlier, right? Then similarly, Hubbard loss is there, pseudo loss is there, okay? Equation, you can actually Google it out, you can get the equation, right? And when it comes to classification part, you will get hinge loss, right? And then cross entropy loss. You will see in my next implementation video that I will be generally using, like, say, binary classification or categorical classification based on the output that I'm supposed to get, right? So this is just a conclusion, okay, that whatever the things that we have understood till now, or this neural network series, right? So I hope that this is actually more than enough, right, in any industry use case, right? I think if you get this, then I think you are a better deep learning engineer, I would say. If I show you the implementation as well, you would able to know that before knowing the ML foundation series, okay, whatever the knowledge base that you have, right, you actually upgraded your knowledge base to something called as deep learning by understanding about the artificial neural network, okay, in a more in-depth manner, okay. So the agenda of the entire lecture series is just to let you know about it, how this neural network work, okay, so that once you go through this, okay, and once you understand this everything, then we will move into the convolution neural network. So in my next video series, it will be mostly focusing on the object detection part. But before object detection, you need to understand about, like, how does, yeah, like, the image classification works. For that, you need to understand about the convolution neural network, its architectures, right? Then we will go with the YOLO model for detecting different objects, right? Then we will go with the segmentation model. We have a three segmentation. We have an instack, synoptic, semantic. So these kind of segmentation model, right? Then we go with the pose estimation model and entire lecture. So this is like just enjoy this complete series. You will get a lot whatever you have asked for. Okay, so thank you, and then let's meet the implementation part of the neural network again. Okay, so till now that we have understood is about the whole nature of neural network, right? The architecture of neural network we have seen, the entire pipeline, that how does the neural network works, right? And how to compile the neural networks, and what are the other things, other tool which we used post training, like optimizer, then we have something called as batch normalization, dropouts. Then we are supposed to do the back propagation method and other thing, right? Now I will show you a very practical demonstration that how to first train the neural network, okay, for which I will be taking the TensorFlow library. Okay, now what will happen is that from the TensorFlow libraries, I will be using the submodel which is called Keras. So why Keras? Because from Keras we can easily actually try to construct a neural network, right, with a very few line of a code. And the other thing is that it contains the very inbuilt optimizers, and it contains a lot of training tool which is actually needed, right? So let's talk about the early stopping method, right? So even like we can do the early stopping in a far more easiest way using a TensorFlow library, okay. So we are supposed to use the few of those basics, which you can actually also visit to the TensorFlow documentation and learn it by yourself. So I will just give you a little glimpse about it. So let me just go and just type like TensorFlow Keras neural network, right? So you can actually see that the sequential model at this one, right? So how you can actually construct your neural network, right? So in this way, like, you will be started constructing your neural network and everything. So let me show you first that what kind of data that I'm supposed to use in order to first train the neural network. Okay, so before that I need some kind of a data. Okay, so let me give you the little glimpse of that data. The data that I'm supposed to take is basically the MNIST fashion data set. Okay, so what does this data set going to tell, right? So it is kind of a supervised learning. It means that it has something called as training, and then something called as training data, as well as its attached label. Okay, so let's say that we have a number of features, and then we have a labels assigned to that feature. Okay, so similarly, let's say that if we have, let's say, 1 lakh images, right? So 1 lakh images of a cloth. Okay, so every cloth has its own type, right? So all the type is actually having a label. Okay, that let's say that if this is a cloth, right? So this first cloth is basically a pullover, the second is trouser, okay, the third is bag. So similarly, whatever the fashion accessories that we have, okay, that is getting labeled into the y-axis. Okay, and these are the necessary features. Okay, so in order to represent it, let's say, into the data format, so how it will look, so let me also give you that thing as well, right? So if you could see this, right, so I have something called as image and label encoding. Okay, which means that I have already an image, I have already encoded the image. Now how we will see it into the next series of video where we will deal with all the convolution neural network, okay, and then how to actually encode the image. For now, just understand that your image has been encoded, okay. So every set of images has been encoded into, let's say, the dimension of 784, okay. So if you could see that this is your tabular data, okay. The first row of the table is containing, let's say, the tabular data, which means the binary encoded data, and then it is actually having a label maximum 784, okay, which means that one image has been just miled down and like boiled down into the 784 dimension, okay. Similarly, for the next image, it is actually boiled down to some other dimension, and every image will be having some kind of a label to it, right? So this the entire data, okay, the size of the data, let's say 80,000 data that we have, okay. So the each data has been labeled with its like category, okay, the image category, right? So basically we are actually training a categorical machine learning model, okay, or I should say the deep learning model, because the neural network is actually attached to it, right? So first of all, we need to train and test our model, correct? Now for training and testing, we need to first split our data set, right? So for splitting, again, we are supposed to use the TensorFlow library as well. So let me just directly hop into the code and then show you everything, right? So as you can see that, first of all, these are the necessary libraries, okay. These are the necessary libraries which is actually needed in order to like do it and go it later implementation, right? So these are actually the necessary libraries which like TensorFlow and then Matplotlib, right? Now the next one which I'm supposed to like import is basically TensorFlow.keras, okay. As I told you, because keras is basically a submodel, right? So inside this submodel, I'm supposed to use like the layer, the model, the regularization parameter, and let's say the loss function, right? So other things you can also implement it by yourself, right? So this is basically the necessary imports, okay. And then Matplotlib is what? Matplotlib is that I want to plot some kind of accuracy matrices or a loss or let's say log loss matrices, then I can actually use the Matplotlib, right? And then NumPy is for the scaling operation of the image, right? So as you can see that I'm actually like using the data set, right? So I'm actually loading the data set, and then the data set has been loaded into X-train and Y-train, right? So let me just show you that what is the shape of this data, right? So let me just show you something like X-train, right? X-train dot shape, right? As you can see that my shape of this data, right, is basically 60,000. It means that I will be having a 60,000 images, and each image is actually, let's say that each image has been like broken down into the multi-dimension, okay. So let's say that I have 60,000 image, and each image is having a 784 number of features, okay. So if you could understand it from the tabular data, it looks something like this, right? So I have one image, okay, and the one image is like uh, like broken down into 784 number of features, okay. So in total, if you wanted to understand in a very tabular perspective, then just understand in this way, that you have a table, okay, and then in this table you have a multiple features, okay. And how many features you have? You have 784 features, okay, and then this is your label data. Similarly, it looks something like this, okay. So it means that you have actually 784 feature, okay, and you have 60,000 images. Got it? Now let's say that if you want to like split it into test, right? So if I just split, so this is my test dot shape, okay. So test dot shape means what? So it contain again, so like the 10% of the data which I wanted to like pick it for this testing model. So it is like 10,000, like the 10,000 images and its label, right? Now if you wanted to see the label, so how can I actually see that? You can just see Y-train. Okay, now tell me what should be the Y-train? The Y-train is actually equals to the number of row, right? So if I just put the Y-train, and then if I just put the Y-train dot shape, so can I expect that it is actually equals to this one, right? One second, let me import it one more time, right? So now it is actually equals to what? It is actually equals to the number of whatever the number of training samples we have, right? So similarly, the same number of training samples I will be having in Y, right? Similarly, let's say that if you wanted to like test it Y test data, right? Y test dot shape, you can actually like visualize the same thing, right? Similarly, let's say that if you wanted to see the first row of the data, so how can you actually see X-train, right? And let's say the first row is something looks like this, right? So yeah, this is basically a first row, okay. Let's say that if you wanted to look into the second row, you can actually see that, okay. So in this way, you will be having the entire 784 data. Okay, so 784 features. So these are basically the features, right? Now let's come to the class name. Okay, that what are the classes that we should define? Okay, because let's say that these are basically class name, right? These are actually the classes, right? If I just wanted to print like what are the length of class, length of class names. Okay, so I will be having total 10 number of classes. It means that whatever the classification model that I will be making, right? So I should be having a 10 classes, okay? So that our actually model should classify any of these 10 classes. Got it? Now, after dividing into the different classes, let's try to make the simple, let's try to construct a simple neural network, right? Now, before constructing the neural network, how many features you have, okay? Or like, let's say that how many inputs you have in one row, you have around 787, right? So it looks something like this, right? So if you just understand that, so I'm actually like using a model, okay? So I'm just using a class, okay? Inside the class, like model class, inside the class, I'm actually calling a method which is called sequential. Now, what does that do? Okay, it is basically try to make a skeleton of the neural network, okay, which means that this is my first layer, okay, this is my first layer. So my first layer is actually containing the 5 number 2, like the 512 number of neurons, okay. Now the second layer is actually containing the 512 number of neurons. It's actually depend upon you. You can actually change the number as well. And let's say the final neuron or the final layer is actually containing the 10 final neuron, okay. And then if you could see that I have already told you that each layer will be having associated activation function. It means that all the, so in the first layer of neural network, so I will be having a 512, like 512 number of input neurons, right? And each neuron will be associated with its activation function, and the kind of activation function that we generally use in the middle layer or in the hidden layer is basically a ReLU activation function, right? And at the last, I am supposed to use the softmax activation function. Why? Because I need to train this model for classification, okay. So you have understood that my data part, that how my data looks like, how to train and test and split the data, and how to construct the skeleton of the neural network, okay. Let me tell you one more time. So now again, this is my base model. So this is my first input layer, this is the second input layer, or this is my final input layer, okay. Now you could ask and raise the question that you have actually this 787 number of input, okay. Now it is not like, it is not impossible to actually like associate, because it is a fully connected, so it is like not possible to connect all the 787 number of neurons, or the input I should say, to the all this hidden layer, because my hidden layer is only 512, okay. So now what I'm supposed to do, that is why I am actually dividing all the 787 number of features into a different batches, okay. So let's say that I have divided into 128 128 128 kind of batches, right? So now let's say that whatever the data, let's say that again for the first row I will be having a 784. So to the entire 784 I cannot directly pass it into the hidden layer, because my hidden layer is actually 512 number of input neurons, right? So what I'm supposed to do is that I am actually dividing it into the different batches, okay. Now once I divide it into the different batches, so I can actually now significantly pass it into my hidden layer, okay. And this is all fully connected neural network, right? So as you can see that all this input layer is getting passed into this, all this 512 neurons, and all this 512 neurons is basically like fully connected to the another hidden layer, okay. And finally you will be having a some set of softmax activation function, right? So because of softmax activation function, I'm actually using this the 10 input hidden layer on, okay, or the output layer, right? So this way I hope you could understand this, the architecture of like how I am actually constructing the neural network using a TensorFlow library, okay. Now let's back to the code. So now as you can see that this is my base model, right? So this is basically my base model, and so this is, yeah. So now what does this will perform, okay. So this compile, right? So base model dot compile, which means that it will try to connect, okay, it will try to connect all the hidden layer to the another hidden layer, okay, because I already told you that these are actually the fully connected neural network, right? So it has to be connected, like first the input layer is actually connected to all the hidden layer, and then hidden layer is further connected to the another hidden layer till it reaches to the last output layer, okay. So this way, and then the optimizer, and then the kind of optimizer that I should supposed to use, okay. So I have a lot of optimizer, right? I have a Adam optimizer, I have SGD optimizer, I have a batch optimizer, batch gradient optimizer, right? So many different, I have RMS prop is also there. So these kind of optimizer is there. So Adam is like most of the neural network architecture, Adam is the most significantly used like activation optimizer. Okay, that is why I've used the Adam optimizer. And then again the loss, because I am supposed to like use the classification problem, so I'm actually using the cross entropy loss, right? So something like this. And then I'm supposed to like measure all these things through accuracy matrix, so I have done this, right? And where I can actually find all these things from the TensorFlow, like the documentation itself. Okay, I'm not doing any rocket science. I'm just referring to the documentation and making the simple neural network. Okay, see how easy it is to make a neural network like this. Okay, right, instead of like writing the big function, you can just like compile it, call the submodule, and then you can actually able to try to construct the entire neural network, right, in just 3 lines of a code, right? Now this is, yeah, and now this is important. Like once you actually like constructed a neural network, now it's chance to basically train your model. Okay, so how can actually train it? Again, your whatever your base model will be, and then it is getting trained into your, let's say, X train. Okay, so let me just use, yeah, this is my X train, Y train. I am actually training for 30 epochs. Okay, batch size I am actually using 128. Why batch size? Because I have a number of hidden layer which is far more greater than the number of input hidden layer. Like the number of input size is actually greater than the number of hidden layer, number of neurons present in the hidden layer. That is why I'm dividing it into the batching. That is why I'm batching it, right? So that is why I'm just dividing it into the different batches, right? And this is basically the validation split. So like in validation data set, which is just a subset of training data set, so I'm just using a 20% of the data into my validation data just to test my trained model. Okay, so that I can just keep my testing model unseen. Okay, and this is basically the verbose. So verbose means like whatever the output you actually see inside this cell, so you are actually activating those verbose. Okay, and after running the 30 epochs, you could actually see the result, right? So this is just I wanted to plot, and you can actually see the result that this model is trained on 30 epoch, and you can see that this is actually your baseline trained model. Okay, so training is around 96%, and let's say the baseline validation is around 85%, right? Now my next question to you is like, can you observe and tell me that whether it is actually overfitting or underfitting? It is actually overfitting, right? Why? Because I have not done anything like extra to my input layer. Okay, I have not added the dropout, I have not added the regularization thing, I have not like normalized using a batch normalization or a layer normalization. I am just simply constructing the neural network, right? And how actually I can identify that this is basically overfitting? Because I can see that I've already told you in my ML foundation lecture as well, right, that my baseline model, right, so my validation loss is actually far more greater than my testing loss. Okay, or my validation accuracy is like much, there is a gap between validation accuracy and a training accuracy. Okay, or you could also like imagine in this way that whatever my validation loss is and whatever my training loss is, okay, there is, let's say, far gap. Okay, there is much gap. Okay, so from this I can actually understand that maybe because my data does not contain, or maybe my neural network is not so much big, right, in order to like get a very clear idea, right, that whether it is actually overfitting or underfitting. Okay, so in order to just reaffirm all these things, what I want is that I want to add some more things. Okay, I want to add, let's say, batch. I want to add the batch normalization. I want to add the dropout ratio. Okay, and then let's try to check that whether I am getting the similar kind of a result or not, right? So as you can see that, so what I'm supposed to do is that I'm actually like loading the batch normalization, because batch normalization I already told you, right, in the previous lecture. To avoid the regularization, actually I'm using the dropout, which means that between like just behind this layer, right, just behind the second layer, I am just like dropping, let's say, or I could say that I am just switching off the 30% of the neurons. Okay, so that every neuron is not getting like overfit to my input data. That is why, right? So yeah, so that is why I'm actually, and why we are not using dropout at the very first layer, because I don't want my input data to completely like I don't want my input data to completely like forget about the everything, because my input data is like the core data. Okay, and suppose at the very first hidden layer, if I'm using the dropout, right, then actually I'm forgetting the entire data itself. Okay, so the core idea of using the dropout is basically like you should use the dropout in the middle of hidden layer, but not at the first layer. the first hidden layer. Just remember this, right? So again, I'm actually training it in the same manner. So if I'm training it by using the dropout, again you will see that this is actually not good, right? Why it is actually not good? Because as you can see that the trend, okay, the trend is like my base validation is like decreasing, okay, decreasing. It's not like carrying the upward trend, it's actually decreasing, and my training, like my training accuracy keeps on increasing, okay, and this is not a good. So I wanted to ask you, like, why would you feel that this is basically a bad model? Okay, so you can actually tell that this is basically a bad model because this model is like in a middle zone. Why it is a middle zone? Because this model is neither too big or not too small. So this model is neither too big to be overfit or not too small to be underfit, right? So just remember this part, right? Because someday you will be getting this. Now let's try to update the model. Okay, let's try to like update some more dense neurons. Okay, so earlier what we were using is that we were using the 512 as an input neuron, right? So now I have just increased the first hidden layer input neuron to, let's say, 2048, right? And similarly, let's say the second hidden layer, the third hidden layer, the fourth. So actually I have added the 4 hidden layer. Again, I am not here using the dropout and batch normalization, okay, or neither I am actually using the early stopping. Why? Because I wanted to show you the penalty of it, that penalty of not using these things, okay, so that you could actually understand it very conceptually, okay. So this is just a simple neural network where I am just, like, for now I am just increasing the number of neurons, that's it, right? So for increasing the number of neuron, again training it, right, I will be getting this gap, right? And this gap is not good. See, the point is, when you confirm that this is basically good, right, when you see that your validation data, like validation accuracy trend is actually moving upward, right, but it is actually going very stagnant, okay, it's actually going in a very one directional, right? So it is not very good, right? Now let's try to improve the model. Okay, so how would you actually improve the model? So let's say before improving this model, I want to like show you one more thing, right? So let's say that if you wanted to see the number of parameters, you can actually also see these things. So let's say that I have this trained 2 model, right? So if I just use it here, so yeah, somewhere here, right? And just I wanted to like print the layers, right? One second. Yeah, this is my base model. This should be base model. Okay, so these many layers I have, right? And let's say that if I wanted to like print the summary of it, so that you can also get the summary. Okay, so you will also get the summary, which means that you will be getting these many number of trainable parameters, right? So in first layer, in second layer, in third layer, so these many parameters you will be getting. So you have your total parameter this, and then you have a trainable parameter is actually this, right? Now again, let's go and improve the model. Okay, now what I'm supposed to do is that, so I will be keeping the number of input neurons from 512 to, let's say, 2048, right? Apart from that, I will be also using some kind of batch normalization, some dropouts. Okay, then again the activation function which I'm supposed to use is basically a ReLU. Okay, and again you will see that again I am getting a result which is not pretty good, right? Unless if I do the early stopping part. I told you in my previous video as well, right, that what is actually early stopping. Early stopping is basically prevent your model to get overfit, okay? Or early stopping is like once your training accuracy is not changing, right, then you should actually stop rather than wasting the number of epochs. So it has many advantage, okay? Or early stopping is, let's say that whenever your validation loss is actually like, let's say, greater than your training loss, right? So at that particular point you should early stop your model, right? So in this way you basically like save the compute as well, right? So for early stopping, again I'm doing the same thing, right? So for early stopping there is a TensorFlow keras and there is a callback, like, so from the TensorFlow I'm actually like using a class called keras. Inside the class I'm actually using the method called callback. Inside the method, let's say, so inside the callback class I'm actually using a method which is like early stopping, right? So early stopping, inside the early stopping I have actually like defined all those things which is basically necessary. You can just go and refer to the documentation, you will find a lot of things and a lot of condition as well to do the early stopping, right? So for now I am just like doing the early stopping like whenever patience equals to 10, which means that after 10 epochs if I see that there is no there is no increase or decrease in accuracy, so I should do the early stopping, right? Now again, let's train the model, right? So after training, so let's say that if I'm training the model with the early stopping, right, the same thing, nothing, so there is nothing like rocket science in it, right? The same thing, the same kind of a skeleton, the same kind of a code. Only thing which I have added is that callback equals to early stopping. Now what it does is that instead of just iterating, let's say the entire 100 epoch, it's basically like stop the model at 16 epoch, that's it, right? And then if I just like if I just visualize the graph, right, so what you will observe, you will basically observe one thing, right? Can you tell me, like, you will basically observe that the somewhere like your baseline validation model, right, and somewhere let's say that your training model, right, so it kind of better compared to previous one, right? Why? Because let's say your baseline model is basically like it basically early stopped, right? So after this is basically stopped. Why? Because rather than going upward, because anyway this model and this model will not going to increase it, right? So like better you actually do the early stop, right? And this model, if you just find out the median of this model, you will get like the accuracy around, let's say 98, 97.5 something accuracy, okay? And then you will get a validation accuracy is around 92%, right? So 92 to 97, which is like only 5% difference, right, between validation accuracy and the testing and the training accuracy, which is kind of good. Now I'll tell you one more thing, just try to understand this part, okay? Just refer this table, okay? And I think as a practitioner you will definitely try to understand this part. Whenever let's say you wanted to like see the training accuracy, right? So let's say that if your training accuracy is let's say 92% to 96%, if you just train your model like regressively, okay, with all the things keeping in mind, right, so you will get a very healthy accuracy around 92 to 96%, right? Now when is the warning? When like your accuracy is actually like moving forward to 97 to 90%, 97 to 99%, okay? So you should actually warn yourself that maybe your model could overfit. That is actually it is giving you the training accuracy, okay? Then other thing is that severe like overfit when it is actually greater than 99.5, because there is a very rare chance that any machine learning model will get these kind of accuracy when it comes to the training accuracy part, right? Then again, the validation accuracy, it should like within 3 to 4% of training, right? 3 to 5% of training, if you could see. So this is kind of a healthy model, I can say, right? Because my validation accuracy is around 3 to 5%. If it is greater than let's say 6 to 10%, then I could say that my validation accuracy is like this model is actually kind of overfitting, right? If you could just see the previous diagram as well, right? So you can see that 85% and 97%, right? So 85 to 97 is the accuracy around more than like 10 to 11% accuracy, okay? So from this I actually like I told myself that maybe my model could overfit. That is why by using the early stopping I can basically control it, right? So this is very important. Now yeah, so now the third part is this one. So the third part is basically the training loss, okay? So let's say that if your training loss is low and still decreasing, okay, then in this case the model is actually over, like it's very healthy, right? It's very good that you're actually like you're getting a graph something like a heartbeat format, okay? You're not getting a graph something like an exponential, right, curve, something like that. And then let's say that if you're let's say that training accuracy is let's say very low, okay, then that is basically a warning. So you can actually refer this table and just try to like try to see it more intuitively, right? That how rather than constructing the neural network blindly, you should do it more smartly, okay? And I think that is the better way of actually like making any neural network construction, right? So similarly, let's say that I wanted to like test it into the regression problem. So again, I will do the same thing. So again, I am going to check the California housing dataset, which means that I need to like do the regression analysis of like finding out the prediction of let's say that the price of the house like in dollar, okay? So I wanted to like predict based on different features, okay? So similarly I am just making one model. So let me show you here you will get it, right? So see, I have already trained this model so that you will get a good insight, right? Yeah, so this model again I am just using the ReLU activation function, and there because it is a regression problem, that is why I am just using a only single output neuron, okay? Only single input neuron is needed. As I told you that kind of activation function that you are supposed to use. So in classification problem and in whether in classification problem or regression problem, okay, I told you before that what kind of activation function you are supposed to use, right? Then these are actually the parameters. Then these are you wanted to make this model more smarter, so how could actually make it, right? using the dropout, using the batch normalization, using the early stopping. Okay, so just understand this keyword, right? So that you could able to like make the any set of model anyway, because this is actually the experimental thing, right? So you need to do it by yourself, you need to practice it by yourself by looking at the documentation, right? By asking questions. I think in this way, yeah, because if I would not have asked question, then I would not have like do the early stopping, right? I will just let my model to complete the iteration of like let's say 100 epochs, which I don't want that, right? That's why. So yeah, and again, like if you wanted to train this model and then finally you will get the output something like this, right? And this is just a like difference between the this like the validation loss and the two model. Okay, so this is like the first model, the second model, and you can actually like find out the difference, right? And you can like try to plot it any number of graph is possible from this, right? So this I actually wanted to show you. Okay, this I actually wanted to show you that both that how to construct a neural network using a TensorFlow Keras library. Okay, then how to do all this operation, how to first like increase the neural network and everything. Let me show you one more thing, which you would get it right. So this is like the neural network visualizer, right? So let's say that if I just do, if I just, you can actually play it around, because that way you will be more conceptually stronger. Okay, so let's say that in hidden layer I wanted to make a 30 neuron. Okay, so yeah, these are basically my 30 neurons. Okay, and input, whatever input you can actually pass, and let's say that I wanted to make something like 12 neuron as a second layer, right? So now let's say the third layer I wanted to make, let's say 50 neuron. Okay, so the third will be actually converted into the 50 neuron, let's say, and then 4. So suppose if it is a binary classification, so like I should have 2 binary classes, let's say yes or no, right? And suppose it is regression classes, I can just make one neuron, that's it. Okay, so if you just try to make it, so this is my 1 neuron. Okay, and after that, let's say you wanted to construct one more thing, let's say I wanted to make a 20 neuron out of it, I will be making the 20 neurons, something like this, right? So this is the way like you can actually like play it around. Let's say that, let me just use it, let me just try to, let's say that if your input size is let's say 50, right? So I will be making, let's say 70 neuron, right? So I will be making the 70 neuron, then again I will be making let's say 40 as a hidden layer, then I will be making let's say 20, I would say, right? Then I will be making let's say 10, and let's say I have a, if I would have been like selected a classification problem, so let's say if it has a 3 classes, then I can just use 3, that's it, right? So in this way you can actually construct the model. Similarly, like let me play one more time. If I will be making 10, then let's say 20, then let's say 8, right? And then 10, and then 3. See, okay, how beautiful it is, right? So you can actually play it around. See, these are actually the hidden layer. See, these are basically the hidden layer. These are the hidden layer, this is the hidden layer. So this is the first hidden layer, second hidden layer, third, fourth, fifth, right? There are actually 5 hidden layer, right? And this will be like weights. Okay, and here you will be passing the inputs. Okay, inputs to your first hidden layer. Okay, and then like the output of the hidden layer is getting passed into the second hidden layer. The output of the hidden layer first will be passed as the input of second hidden layer. Similarly, the output of the hidden layers second will be passed as the input of third hidden layer. Okay, and I told you about everything, like the activation function, how to construct the matrices, right? Then how to do a dropout, how to do the early stopping, right, to avoid the overfitting issue, you know, how to do the regularization, right, how to pick the problem which is like supervised and unsupervised way, how to train it using a TensorFlow Keras, right? So everything, so that you can actually implement it by yourself. Okay, so just let me know and just try it first yourself, and just let me know if you want anything. I will happy to make the another video into this topic. Thank you.